Hello, and welcome to the channel. Tonight we're stepping into the vast, unexplored world of our planet's hidden oceans. Picture our blue marble from space, where 3/4 of its surface shimmers with water, yet beneath those familiar waves lies a frontier more mysterious than the surface of Mars. Imagine mountain ranges taller than Everest, canyons deeper than the Grand Canyon, and entire ecosystems thriving in perpetual darkness, all existing in a realm where human footsteps have never fallen. It's a world of liquid space, where every descent reveals new wonders and ancient secrets, mysteries that unfold one patient moment at a time. Before we begin, if you enjoy drifting off to the gentle hum of science, I'd be very grateful if you tap the like button and subscribe to the channel. It helps more sleepy minds find their way here. And while you're settling in, I'd love to know where you're watching from and what time it is for you right now. Feel free to share it in the comments. It's always wonderful to see how far these quiet little journeys reach. So get cozy, let your shoulders relax, let your thoughts drift down like marine snow settling through the deep blue silence, the great blue unknown, why most of the ocean remains a mystery. Picture this. You're standing on a beach at sunset, watching waves roll endlessly toward the horizon. The ocean stretches before you like a vast, breathing blanket, beautiful and serene. Children are building sandcastles nearby, and the salt air fills your lungs with each gentle breath. It feels familiar, almost comforting. But here's something that might change how you see that peaceful scene forever. Beneath those rolling waves lies the most mysterious, unexplored realm on our planet. While you've been watching rockets launch toward Mars and rovers traverse alien landscapes, 95% of Earth's oceans remain as unknown to us as the surface of distant moons. Think about that for a moment. We know more about the craters of our celestial neighbor than we do about the deepest parts of our own blue world. The ocean isn't just water, it's a three-dimensional universe, layer upon layer of liquid mystery stacked from the surface down to crushing depths that would flatten a human in an instant. Imagine if our entire understanding of land came only from observing the tops of trees while everything below the forest floor, the root systems, the underground rivers, remained completely hidden from view. That's essentially our relationship with the ocean. We've mapped every street corner of major cities, catalogued millions of stars, and can predict weather patterns weeks in advance. Yet the seafloor beneath our feet remains largely anonymous. It's like living in a house for your entire life, while never opening the basement door, never knowing what treasures or terrors might be waiting just below the floorboards. The numbers tell a staggering story. Of the ocean's 1.3 billion cubic kilometers of water, we've explored less than 5%. That means 95% remains untouched by human eyes, unexplored by human technology, unknown to human understanding. To put this in perspective, imagine if you could only see 5% of your neighborhood, maybe just the streetlights and the tops of chimneys, while everything else remained shrouded in perpetual fog. But why does this matter? Why should we care about exploring a realm that seems so disconnected from our daily lives on land? The truth is, the ocean isn't separate from us at all. It's intimately connected to every breath we take, every drop of rain that falls, every climate pattern that shapes our world. The ocean is Earth's pulse, its memory, its vast liquid heart pumping life and weather and mystery through every corner of our planet. Every wave that reaches that peaceful beach carries stories from the deep. Stories of creatures that have never seen sunlight, of underwater mountains taller than Everest, of temperatures and pressures that would seem impossible on the surface. The ocean holds Earth's history in layers of sediment, like pages in an ancient book, written in a language we're only beginning to understand. When marine biologists venture into the deep with their submarines and robotic explorers, they return with tales that sound like science fiction, creatures that create their own light in a world of eternal darkness. Fish that live under pressures that would crush a submarine like a tin can. Entire ecosystems thriving around volcanic vents, powered not by sunlight but by the heat of Earth's molten core. And yet, for all our technological prowess, for all our satellites and supercomputers and space telescopes, we remain largely blind to this underwater universe. It's humbling, really. This reminder that mystery still exists on our familiar blue marble while we dream of colonizing Mars. The deepest parts of our own ocean remain as alien and inaccessible as any distant planet. The ocean keeps its secrets jealously, protected by barriers that seem almost intentional. Crushing pressure, absolute darkness, and distances so vast that they swallow our best efforts to explore them. It's as if Earth itself has reserved one last frontier, one final mystery for us to slowly, carefully unravel. But that mystery calls to something deep in the human spirit, the same curiosity that drove our ancestors to climb mountains and cross continents now pulls us toward the abyss. We know that down there in those unexplored depths lie answers to questions we haven't even learned to ask yet. And perhaps most intriguingly, we know that the ocean still has the power to surprise us, to show us that our small blue world still holds wonders beyond our wildest imagination. Beneath the surface, where exploration stops and mystery begins, think back to the last time you took a deep breath and dove underwater, maybe in a swimming pool or at the beach during a summer vacation. Remember that moment when the noise of the surface world suddenly muffled, when everything became quiet and blue and strange. You probably held your breath for 30 seconds, maybe a minute if you were determined, before your lungs demanded that you return to the world of air and light. That brief dive, that moment of submersion, represents the extent of natural human exploration of the ocean. Without technology, without artificial aids, we are creatures of the surface, forever bound to the thin layer where water meets air. We are like birds, trying to understand the forest by only skimming the treetops. But let's follow that diving experience a little deeper, shall we? Imagine you could somehow keep descending past the point where your lungs would normally force you back up. At first, the water around you would still catch and scatter sunlight, painting everything in shifting patterns of blue and green. Fish would dart past, familiar creatures from aquariums and nature documentaries. You might see seaweed swaying like underwater trees, or coral formations that look like alien cities built for tiny inhabitants. This is the sunlight zone, the oceanic neighborhood where most of our ocean exploration takes place. It extends down about 200 meters, roughly the height of a 60-story skyscraper. If the ocean were a skyscraper, this sunlight zone would be just the penthouse floors, the luxury apartments with the best views. Everything below? That's where the mystery begins. Human beings, despite all our innovations and ambitions, remain fundamentally surface creatures. Our bodies are designed for air pressure, for the gentle squeeze of atmosphere that we've lived with for millions of years of evolution. The moment we descend more than a few meters underwater, our bodies begin to rebel. Our lungs compress, our sinuses ache, our ears pop with pressure changes that feel increasingly urgent. Even the most skilled free divers, those remarkable humans who train their bodies to descend on a single breath, rarely go deeper than 100 meters. That's extraordinary by human standards, equivalent to diving down a 30-story building while holding your breath, but it's still just scratching the surface of oceanic possibility. It's like trying to understand the entire atmosphere by jumping as high as you can and looking around. The ocean has layers, you see, like a vast vertical ecosystem stacked in zones of increasing mystery. Each layer has its own personality, its own rules, its own strange communities of life, and the deeper you go, the more alien it becomes, until you reach depths where the very concept of surface becomes meaningless, where creatures exist that have never known sunlight, where pressures mount that would instantly crush anything from our familiar surface world. This is where our human limitations become painfully obvious. We need air to breathe, warmth to survive, and light to see. The deep ocean offers none of these things. It's cold, dark, and filled with pressure that increases relentlessly with every meter of descent. It's like trying to explore another planet while wearing only a bathing suit. Even our technology struggles with this alien environment. Submarines, those marvels of engineering that we think of as deep-sea explorers, can only reach a fraction of the ocean's depth before the pressure becomes too much for their metal hulls. It's a humbling reminder that for all our cleverness, the ocean sets its own rules, and those rules are unforgiving. But here's what makes it even more fascinating. The point where our exploration stops is precisely where the ocean's most incredible secrets begin, just beyond our reach, just past the edge of comfortable human exploration, lies a world so strange and wonderful that it challenges our understanding of what life on Earth can be. It's as if the ocean has drawn a line in the water and whispered, "Everything interesting happens below here." The creatures that live in these deeper zones have evolved solutions to problems we can barely imagine. They've learned to create light in a world of darkness, to find food in a realm where nothing falls from above, to survive pressures that would turn us into something unrecognizable. They've become aliens on our own planet, living just beneath our feet in a world we can visit, only briefly, and only with the most sophisticated technology we can create. And so the great irony emerges: the most mysterious unexplored realm on our planet lies not light years away among distant stars, but right here beneath us, separated from our familiar world by nothing more than water and depth. And the fundamental limitations of being human. The abyss begins where our exploration ends, and it holds secrets that we're only beginning to imagine. The crushing pressure and total darkness, the ocean's natural defense. Imagine trying to hold up the weight of 50 jumbo jets with your bare hands. That's the pressure your body would experience just 500 meters below the ocean's surface, roughly the depth of the Empire State Building, if it were somehow submerged. And that's still considered the shallow end of the ocean's mysteries. Every 10 meters you descend into the ocean adds another atmosphere of pressure, roughly 14.7 pounds per square inch pressing in from all directions. It's like nature's own security system, an invisible wall that grows stronger and more formidable with every step down into the abyss. By the time you reach the average depth of the ocean floor, about 4,000 meters down, you're dealing with pressure that's 400 times greater than what we experience on the surface. To understand what this means, picture your body as a balloon. On the surface, that balloon maintains its shape, because the pressure inside matches the pressure outside. But start descending into the ocean, and it's like placing that balloon inside a hydraulic press that slowly, inexorably tightens. Your lungs would compress to the size of marbles, your sinuses would collapse. Any air-filled space in your body would be squeezed smaller and smaller until, well, let's just say that humans weren't designed for this environment. But pressure is just one of the ocean's defenses. The other is even more fundamental: darkness. Not the kind of darkness you experience when you turn off the lights in your bedroom. The kind of darkness where you can still see shapes and shadows, where your eyes slowly adjust and begin to make out familiar objects. Ocean darkness is absolute, complete, eternal. Sunlight, that life-giving energy that powers almost everything we know on the surface, can only penetrate so deep into water. In the clearest ocean water, under perfect conditions, sunlight might reach down 200 meters before fading to nothing. That's like trying to illuminate the bottom of the Grand Canyon with a birthday candle. Below 200 meters, the ocean enters perpetual night, a darkness that has lasted for billions of years, unbroken by any natural light from above. This isn't just an inconvenience, it's a fundamental reshaping of reality. Think about how much of your understanding of the world depends on sight, on light, on the visual information that streams constantly into your brain. In the deep ocean, that entire sensory system becomes useless. It's like trying to navigate a vast three-dimensional maze while blindfolded, with the added challenge that the maze is filled with water and crushing pressure. The combination of these two factors, pressure and darkness, creates what oceanographers sometimes call the wall. It's an invisible barrier that has protected the deep ocean from human exploration for most of our existence as a species. While our ancestors were exploring continents, building civilizations and mapping the surface of their world, the deep ocean remained as inaccessible as the surface of distant planets. Even today, with all our technology, this wall remains formidable. The submarines that can withstand deep ocean pressure are marvels of engineering, with walls thick enough to stop bullets and viewing ports made from materials stronger than steel. But even our best deep-sea vessels can only carry us so deep before the ocean's pressure overcomes our technology. The deepest parts of the ocean, places like the Mariana Trench, require specially built vehicles that can withstand pressures equivalent to having the entire weight of the atmosphere pressing down on every square inch of surface area, multiplied by 1,000. But here's what makes this even more remarkable. Life has found ways to thrive in this seemingly impossible environment. While pressure and darkness would kill surface creatures instantly, deep ocean life has evolved to not just survive but flourish under these conditions. To them, our surface world with its low pressure and blazing sunlight would be as lethal as the deep is to us. Deep-sea fish have bodies that are perfectly adapted to high pressure. They don't have air-filled swim bladders that would collapse. Instead, they've evolved entirely different ways to control their buoyancy, Their bodies are often filled with specialized fluids and tissues that remain stable under crushing pressure. Some deep-sea creatures are essentially living hydraulic systems, perfectly engineered for an environment that would instantly destroy us. And in that eternal darkness, life has learned to create its own illumination, bioluminescence. The ability to generate light through chemical reactions becomes not just useful but essential for survival. Deep-sea creatures turn themselves into living lanterns, creating patterns of light that serve as communication, hunting tools, and defense mechanisms. They've built their own constellation of lights in the endless night of the deep ocean. The ocean's natural defenses, pressure and darkness, have created one of the most alien environments on our planet. It's a realm where the familiar rules of surface life don't apply, where creatures have evolved solutions to problems that surface life never had to face. And it's this alien quality that makes the deep ocean so fascinating and so mysterious. The very barriers that kept us out for so long have preserved a world unlike anything else on Earth, a world that continues to surprise us every time we manage to peek behind the wall of pressure and darkness. The abyssal zone, a world without sunlight. There's a place on our planet where night has lasted for 4 billion years. Not the kind of night that ends with sunrise, but eternal, absolute darkness that has never been broken by natural light. This is the abyssal zone, the deep ocean realm that begins roughly 4,000 meters below the surface and extends down into trenches, so deep they could swallow entire mountain ranges without a trace. To reach the abyssal zone, you would have to descend through more than 2 miles of water past the point where the last traces of sunlight fade to black, past the realm where any surface creature could survive, into a world so alien that scientists are still discovering how different life can be when freed from the rules that govern the surface world. The word abyssal comes from the Greek word for bottomless, and when early oceanographers first contemplated these depths, bottomless is exactly what they seem to be. The ocean floor at these depths was so far down, so unreachable, that it might as well have been the edge of the world. Even today, with all our technology, the abyssal zone remains more mysterious than the surface of Mars. But here's what makes the abyssal zone truly remarkable. It's not empty. Far from being a barren wasteland, it's home to one of Earth's largest ecosystems, a sprawling community of life that exists entirely independent of the sun. While every ecosystem you've ever seen depends ultimately on sunlight for energy, the abyssal zone has learned to thrive on something entirely different. The temperature in the abyss hovers just above freezing, typically between 1 and 4 degrees Celsius. That's like living inside a refrigerator, constantly, forever. There's no seasonal variation, no warm afternoons or cool evenings. Just eternal cold that would kill most surface life within minutes. Yet, the abyss isn't frozen because the immense pressure prevents ice from forming in the normal way. It's a world of liquid cold, where water remains fluid under conditions that seem almost supernatural. The pressure at these depths is so intense that it would crush a human instantly. But the creatures here have never known anything else. Their bodies are perfectly adapted to these conditions. They would literally explode if brought rapidly to the surface, expanding like deep-sea balloons as the pressure that has shaped their entire evolutionary history suddenly disappears. Food in the abyss comes from above, drifting down like snow from the surface world thousands of meters overhead. Scientists call it marine snow, a constant gentle fall of organic particles, dead plankton, and other biological material that sinks through the water column. But this snow is sparse and unpredictable. Imagine trying to survive by catching random crumbs that someone drops from a skyscraper roof, and you'll get some idea of the challenge. This scarcity has shaped every aspect of abyssal life. Creatures here have evolved to be incredibly efficient, able to survive on minimal food for extended periods. Many have enormous mouths compared to their body size, ready to swallow anything edible that might drift their way. Others have learned to be both predator and scavenger, taking advantage of every possible source of nutrition in this food-poor environment. But perhaps the most remarkable adaptation is bioluminescence. In a world without sunlight, life has learned to create its own illumination. Many abyssal creatures can generate light through chemical reactions, turning themselves into living flashlights, disco balls, and neon signs. Some use their light to hunt, creating glowing lures to attract prey in the darkness. Others use light for communication, flashing messages to potential mates or rivals in patterns we're only beginning to understand. The seafloor of the abyssal zone is a landscape unlike anything on the surface. Vast plains of sediment stretch for thousands of miles, broken by underwater mountains, deep trenches and geological formations that dwarf anything on land. These sediments have been accumulating for millions of years, creating archives of Earth's history that go back to the age of dinosaurs and beyond. Moving across this landscape are creatures so strange they seem designed by alien intelligence. Sea cucumbers, the size of small dogs, crawl along the bottom, processing sediment like living vacuum cleaners. Tripod fish balance on elongated fin rays, standing motionless in the current, like underwater birds of prey. Giant amphipods, shrimp-like creatures, the size of rabbits, scuttle through the darkness, their bodies transparent except for their glowing eyes. And then there are the giants. The abyssal zone is home to some of the largest invertebrates on Earth. Giant tube worms that grow to be taller than humans, their bodies anchored around volcanic vents. Colossal squid, with eyes the size of dinner plates and tentacles lined with rotating hooks instead of suction cups. Spider crabs with leg spans that could reach across a dining room table. These creatures live their entire lives in darkness, in cold, under crushing pressure, in a world so removed from ours that they might as well inhabit another planet. Yet, they're sharing our Earth, living and reproducing and evolving in the largest ecosystem on the planet, an ecosystem that remained completely unknown to us until just a few decades ago. The abyssal zone challenges our fundamental assumptions about life itself. It shows us that biology is far more creative and adaptable than we ever imagined, that life can flourish under conditions we would consider absolutely impossible. It's a reminder that even on our familiar blue world, there are still realms so alien that they expand our understanding of what it means to be alive. Technology's limit, why we can't just dive deeper. Every summer, millions of people strap on scuba gear and descend into the ocean's upper layers, marveling at coral reefs and swimming alongside colorful fish. With a tank of compressed air and some basic equipment, recreational divers can explore down to about 40 meters, the height of a 10-story building. It feels like a remarkable achievement, this ability to breathe underwater and move freely in 3 dimensions, but that 40-meter recreational limit represents less than 1% of the ocean's average depth. It's like being able to jump 3 feet high and thinking you've conquered the sky. The ocean's true depths begin where our technology starts to struggle, where the familiar rules of engineering meet forces that can crush submarines like empty soda cans. The challenge isn't just about going deeper, it's about surviving deeper. Every additional meter of depth adds roughly 10,000 pascals of pressure, which might not sound like much until you realize that's equivalent to adding the weight of a small car, pressing down on every square meter of surface area. By the time you reach 1,000 meters down, you're dealing with pressures that exceed 100 times what we experience at sea level. Human technology has always been designed for the surface world, where air pressure is gentle and consistent. Our metals, plastics, and electronic systems are engineered to work under conditions that barely exist in the deep ocean. Take something as simple as a flashlight, essential for seeing in the deep ocean's darkness. At depth, the water pressure will compress any airspaces inside the device, potentially flooding the electronics or crushing the housing. Even waterproof seals designed for swimming pools fail catastrophically under deep ocean pressure. The submarines that can reach the deep ocean are marvels of engineering, but they're also incredibly specialized and expensive machines. The hull of a deep-sea submersible must be thick enough to withstand crushing pressure while remaining light enough to achieve neutral buoyancy. The materials must be incredibly strong but also precisely manufactured. A single flaw or imperfection could create a weak point that would fail catastrophically under pressure. These deep-sea vehicles are essentially miniature spacecraft, designed to protect their human occupants from an environment as hostile as the vacuum of space. They have life support systems to maintain breathable air, heating systems to combat the near-freezing temperatures of the deep, and incredibly strong viewing ports that allow occupants to see outside without compromising the hull's integrity. But even our best deep-sea submarines can only reach a fraction of the ocean's depth. The deepest diving manned submersibles can reach about 4,000 meters, impressive by human standards, but still less than half the depth needed to reach the bottom of the ocean's deepest trenches. It's like building a ladder to reach the moon and stopping halfway. Electronics pose their own challenges in the deep ocean. Water and electrical systems don't mix well under normal circumstances, and the extreme pressure of the deep makes waterproofing incredibly difficult. Traditional electronic components can be crushed or flooded, And even successfully sealed electronics must deal with the effects of extreme pressure on their internal components. Temperature adds another layer of complexity. The deep ocean is perpetually cold, just a few degrees above freezing. This cold can make materials brittle, slow chemical reactions, and affect the performance of everything from batteries to hydraulic fluids. Equipment that works perfectly on the surface may fail completely when subjected to the deep ocean's combination of pressure and cold. Communication becomes almost impossible at depth. Radio waves, which work well in air and space, can't penetrate more than a few meters of seawater. Underwater vehicles must rely on acoustic communication, essentially underwater sound signals, which is much slower and less reliable than radio communication. It's like trying to have a conversation by shouting across a crowded room while underwater. The result is that deep ocean exploration requires incredibly sophisticated, expensive, and specialized equipment. Each deep-sea mission costs hundreds of thousands, or even millions of dollars, and the vehicles involved represent decades of engineering development and testing. It's not like exploring a cave or climbing a mountain, where individual adventurers can push boundaries with relatively simple equipment. And even when we do manage to reach the deep ocean, our visits are brief and limited. Deep-sea missions are measured in hours, not days or weeks. The vehicles can carry only limited supplies, and the risk of equipment failure in such a hostile environment means that every mission must be carefully planned and executed with multiple backup systems. This technological challenge helps explain why we've explored so little of the ocean. It's not that we lack curiosity or ambition, it's that the ocean itself presents engineering challenges that push the limits of human technology. Every meter deeper we go requires exponentially more sophisticated solutions to problems that simply don't exist on the surface. But perhaps most importantly, the ocean doesn't forgive mistakes. A minor equipment failure on land might be inconvenient. The same failure in the deep ocean can be catastrophic. This harsh reality means that deep ocean exploration proceeds slowly and carefully, with extensive testing and preparation for each new depth record or technological advancement. The ocean's depths remain largely unexplored, not because we don't want to explore them, but because they represent one of the most challenging environments for human technology anywhere on Earth. We've learned to fly through the air, travel through space, and explore the surfaces of other planets, but the deep ocean continues to push our engineering capabilities to their absolute limits. The cost of curiosity. Why ocean exploration is so expensive. Imagine if every time you wanted to visit your neighbor's house, you had to first build a spacecraft capable of surviving in an alien environment, train for months to operate complex life support systems, and spend several $1 million just for a brief visit that might last a few hours. This is essentially what deep ocean exploration costs, and it helps explain why we know more about the surface of Mars than we do about the deepest parts of our own planet. The numbers are staggering. A single deep-sea research mission can cost anywhere from $50,000 to over $1 million per day, depending on the depth and complexity of the expedition. The most advanced deep-sea submersibles cost $40 million to build, and that's before you factor in the specialized support ships, crews, and equipment needed to operate them safely. Compare this to space exploration, which we often think of as incredibly expensive. The Mars rovers, those marvels of engineering that capture our imagination with their photographs from another planet, cost roughly $2.5 billion for the entire mission, from development to landing to years of operation. The comparable deep-sea exploration program, visiting and studying the deepest parts of Earth's oceans with similar thoroughness, would cost significantly more and would need to be repeated in thousands of locations instead of just one. The root of this expense lies in the unique challenges of the deep ocean environment. Unlike space, where the primary challenge is the vacuum and radiation, the ocean presents a combination of problems that each require expensive solutions. Pressure resistance means using exotic materials and precision manufacturing. Corrosion resistance requires specialized alloys and coatings that can withstand the ocean's aggressive chemistry. The need for artificial lighting, life support, and communication systems adds layer upon layer of complexity and cost. Every component of a deep-sea vehicle must be engineered to perfection. There are no hardware stores at 4,000 meters depth, no rescue services if something goes wrong, no opportunity to make repairs with improvised materials. Everything must work flawlessly from the moment it enters the water until it returns to the surface, because failure at depth can mean not just mission failure, but potential loss of life and equipment worth tens of millions of dollars. The specialized nature of deep ocean equipment means there's no economy of scale. While we build thousands of airplanes and cars, spreading development costs across many units, deep-sea vehicles are often built one at a time, custom designed for specific missions. Each submarine is essentially a prototype, incorporating the latest technology, but also carrying the full burden of development costs. The support infrastructure is equally expensive. Deep-sea missions require specialized ships, equipped with cranes capable of lifting multi-ton submersibles, dynamic positioning systems that can hold a vessel steady in ocean currents, and communication equipment that can maintain contact with vehicles thousands of meters below. These ships cost hundreds of thousands of dollars per day to operate, and they need to be staffed with highly trained crews who understand both maritime operations and complex scientific equipment. Then there's the human element. Operating in the deep ocean requires specialists, pilots trained to handle submersibles under extreme conditions, engineers who understand the complex systems that keep humans alive under crushing pressure, scientists who can make the most of brief opportunities to study the deep ocean environment. Training these specialists takes years and costs hundreds of thousands of dollars per person. The research itself is expensive in ways that land-based science isn't. Every sample brought up from the deep represents hours of expensive ship time, specialized collection equipment, and careful handling to preserve specimens that may have come from environments unlike anything else on Earth. A single jar of deep-sea mud might cost more to collect than entire terrestrial research projects. But perhaps the most challenging aspect of deep ocean exploration costs is their unpredictability. Weather can delay missions for weeks, adding enormous costs as expensive ships and crews wait for suitable conditions. Equipment failures can end missions prematurely, meaning that months of preparation and millions of dollars in expenses yield only partial results. This economic reality creates a harsh truth. Deep ocean exploration is largely limited to well-funded government agencies and major research institutions. Private individuals, non-profit organizations, and smaller research groups simply can't afford the entry costs. It's as if the ocean has created a financial barrier as formidable as its physical ones. The result is that deep ocean research proceeds at a pace limited not by our curiosity or our technology, but by our budgets. Every dive must be justified in terms of cost versus scientific return. Every mission must compete with other research priorities for limited funding. We explore the deep ocean not as thoroughly as we'd like, but as thoroughly as we can afford. This economic constraint means that vast areas of the ocean remain unexplored, simply because we haven't yet found the funding to visit them. The deep ocean holds secrets that could revolutionize our understanding of life, climate, and Earth's history, but many of those secrets will remain locked away until we find ways to make deep ocean exploration more affordable and accessible. It's a peculiar situation. The largest ecosystem on our planet, the realm that most influences our climate and weather, remains largely unexplored, not because it's impossible to reach, but because it's too expensive to visit regularly. The cost of curiosity about our own planet's depths has become one of the primary barriers to understanding the world we live on. On Echoes in the Deep, mapping the seafloor with sound. Close your eyes and try to navigate your bedroom in complete darkness. You'll probably find yourself moving slowly, hands outstretched, feeling for familiar furniture and walls. Now imagine trying to map an entire continent this way in absolute darkness, while floating in water, under crushing pressure that would destroy most equipment. This is essentially the challenge of mapping the seafloor, and it's why we've had to become masters of using sound as our eyes in the deep ocean. Sound behaves differently underwater than it does in air. In the ocean, sound waves travel about 4 times faster than they do through air, and they can travel for thousands of kilometers without losing their clarity. This property has become our most powerful tool for exploring the deep ocean without actually going there, a way of seeing through water using nothing but echoes. The principle is elegantly simple, like a sophisticated version of the echolocation that bats use to hunt insects. A research ship sends out sound pulses, acoustic pings toward the seafloor. These sound waves travel down through the water column at a known speed, bounce off the bottom and return to sensitive listening equipment on the ship. By measuring the time it takes for each ping to make the round trip, computers can calculate the exact distance to the seafloor at that point. But modern seafloor mapping goes far beyond simple depth measurements. Advanced sonar systems, the technical term for this sound-based mapping, can tell us about the texture and composition of the seafloor by analyzing how sound waves bounce back. Soft sediments absorb and scatter sound differently than hard rock. Smooth surfaces create different echo patterns than rough or jagged terrain. By reading these acoustic signatures, scientists can build detailed pictures of seafloor geology without ever collecting a physical sample. The most sophisticated systems use multiple beams of sound simultaneously, creating what's called multi-beam sonar. Instead of sending out a single ping straight down, these systems send out dozens or even hundreds of sound beams in a fan pattern, mapping a wide swath of seafloor with each pass. It's like replacing a single flashlight beam with a powerful floodlight, illuminating much more area with each sweep. The detail these systems can achieve is remarkable. Modern multi-beam sonar can detect features on the seafloor as small as a few meters across, even from depths of thousands of meters. That's equivalent to being able to spot a car-sized object from the top of Mount Everest, except you're doing it in complete darkness using only sound waves. But sound-based mapping has revealed far more than just the shape of the seafloor. The echoes have shown us an underwater landscape that rivals anything on the surface world. Underwater mountain ranges stretch for thousands of kilometers, with peaks taller than Everest rising from abyssal plains. Vast canyons cut through the seafloor, some deeper and wider than the Grand Canyon. Volcanic seamounts dot the ocean floor like underwater islands, many of them active and creating new seafloor through ongoing eruption. The mid-ocean ridges, underwater mountain chains that ring the globe like the seams on a baseball, were first mapped in detail using sound. These ridges turned out to be where new seafloor is being created, as molten rock from Earth's interior pushes up through the ocean floor. The discovery revolutionized our understanding of how Earth's surface works, revealing that the seafloor is constantly being renewed and recycled in a process called plate tectonics. Sound mapping has also revealed the true scale of ocean trenches, the deepest parts of Earth's surface. The Mariana Trench, deepest of them all, plunges down more than 11,000 meters below sea level. That's deeper than Mount Everest is tall, a chasm so profound that if you dropped Mount Everest into it, the peak would still be more than a mile underwater. But perhaps most intriguingly, sonar mapping sometimes reveals things that shouldn't be there. Shipwrecks appear as geometric anomalies on the natural seafloor, their artificial shapes clearly distinguishable from natural rock formations. Ancient riverbeds, now flooded by rising seas, show up as meandering channels cutting across continental shelves. Sometimes the sonar reveals features so unusual that they require follow-up visits by deep-sea vehicles to understand what they might be. The process of mapping the seafloor is painstakingly slow. Research ships must travel at relatively modest speeds to collect high-quality sonar data, and the ocean is vast. A single research vessel might take decades to map an area the size of a small country, with only a handful of ships capable of deep ocean mapping operating worldwide. The task of creating a complete map of Earth's seafloor becomes almost overwhelming in its scope. This is why, despite decades of sonar mapping, we still have better maps of Mars than we do of our own ocean floor. The red planet can be mapped by satellites orbiting overhead, photographing and analyzing the entire surface over a period of months. Earth's ocean floor must be mapped laboriously, one sonar sweep at a time, by ships that can only cover tiny fractions of the ocean during each expedition. Yet each acoustic ping, each echo returning from the deep, adds another piece to the puzzle of understanding our planet's hidden landscape. Sound waves are becoming our underwater eyes, revealing a world beneath the waves that is every bit as complex, dramatic, and mysterious as any landscape on the surface. Through the patient art of listening to echoes, we're slowly illuminating the largest and least known realm on Earth. Aliens on Earth, the bizarre creatures we've found so far. Every time scientists return from the deep ocean, they bring back photographs and specimens that look like they were designed by an alien intelligence. Creatures so strange, so unlike anything in our surface experience, that they challenge our fundamental understanding of what life on Earth can look like. These aren't science fiction monsters, they're our neighbors, sharing the same planet, breathing the same ocean, living lives so different from ours that they might as well inhabit another dimension. Consider the vampire squid, a creature whose name alone sounds like something from a horror movie. But this deep-sea resident is actually quite gentle, drifting through the darkness with fins that look like delicate wings. When threatened, it doesn't attack. Instead, it turns itself inside out, revealing rows of spines that make it look like a living cactus floating in space. Its eyes, proportionally the largest of any animal on Earth, gather every available photon in an environment where light is more precious than gold. Then there's the barrel eye fish, a creature so transparent you can see its brain through its skull. Its tubular eyes point upward through its clear head, constantly scanning the waters above for the silhouettes of prey against the faint light filtering down from far above. It's like having a living submarine periscope, perfectly adapted for hunting in a world where up and down make all the difference between finding food and going hungry. The anglerfish takes the concept of dinner invitation to disturbing new levels. Female anglerfish carry a bioluminescent lure, a fishing rod made of flesh and light, that dangles in front of their enormous mouths. In the perpetual darkness of the deep, this glowing lure attracts smaller fish, like moths to a flame. Except the flame is attached to a mouth full of needle-sharp teeth. The males of some anglerfish species have evolved an even stranger lifestyle. They're much smaller than the females, and spend their lives as permanent parasites, fusing their bodies to their mates, and essentially becoming living sperm banks. Giant tube worms cluster around underwater volcanic vents, like alien flowers in a poisonous garden. These creatures have no mouths, no stomachs, no digestive systems as we understand them. Instead, they formed partnerships with bacteria that live inside their bodies, converting the toxic chemicals spewing from volcanic vents into usable energy. They're living chemical factories, thriving on substances that would kill surface life instantly. The Dumbo octopus glides through the deep ocean using fins that look exactly like elephant ears, propelling its gelatinous body with gentle undulations that seem almost dreamlike. Unlike their shallow water cousins, Dumbo octopi are surprisingly delicate creatures, their bodies adapted to the constant pressure of the deep. They move like living parachutes, drifting on ocean currents, and occasionally flapping their ear-like fins to change direction. Bioluminescence, the ability to create light through chemical reactions, becomes not just common in the deep ocean but almost universal. In a world without sunlight, creatures have learned to become their own light sources. Some use their illumination for hunting, creating glowing lures to attract prey. Others use it for communication, flashing complex patterns that might be the equivalent of underwater conversation. Still others use light as a defense mechanism, creating bright flashes to confuse predators or ejecting clouds of glowing particles like underwater fireworks. The deep ocean is home to some of the most extreme size variations on Earth. Microscopic organisms drift alongside creatures that dwarf anything on the surface. Giant siphonophores, colonial organisms made up of thousands of individual animals working together, can stretch longer than blue whales. Some specimens reach over 150 feet in length, making them among the longest animals on Earth. Yet they're so delicate and transparent that they're almost impossible to see unless illuminated by submarine lights. Deep-sea gigantism is a common phenomenon, where creatures grow much larger than their shallow water relatives. Giant isopods look like enormous pillbugs, some reaching over a foot in length. These scavengers crawl across the seafloor like alien tanks, their segmented bodies and multiple legs making them look more like something from Mars than Earth. They can survive without food for years, their metabolism slowed to an almost hibernation-like state. The gulper eel takes the concept of all mouth to its logical extreme. Its jaws can unhinge to swallow prey much larger than itself, and its stomach can stretch to accommodate meals that might not come along for months. When food is scarce in the deep ocean, being able to eat anything that comes within reach, regardless of size, becomes a crucial survival advantage. Perhaps most unsettling are the creatures that seem to have no fixed form at all. Many deep-sea organisms are gelatinous, their bodies more like living water than anything we'd recognize as flesh. They drift and pulse and undulate through the darkness, sometimes transparent, sometimes glowing with their own light, sometimes changing shape as they move. They challenge our basic assumptions about what an animal should look like, reminding us that our surface-based ideas of biology represent only a tiny fraction of life's possibilities. These creatures have evolved in complete isolation from the surface world, shaped by evolutionary pressures that simply don't exist anywhere else on Earth. They've had millions of years to develop solutions to problems that land animals never had to face. How to find food in perpetual scarcity, how to find mates in endless darkness, how to avoid being eaten when there's nowhere to hide. Every deep-sea expedition brings back new species, creatures so strange that scientists sometimes struggle to figure out where they fit in the tree of life. It's estimated that we've discovered less than 1% of deep-sea species, meaning that the vast majority of these alien-like creatures remain completely unknown to science. The deep ocean may contain more biodiversity than all terrestrial ecosystems combined, yet most of these life forms remain as mysterious to us as if they lived on distant planets. The deep ocean teaches us that life is far more creative, adaptable, and bizarre than our surface experience could ever suggest. These creatures aren't just curiosities, They're proof that biology operates by rules we're still learning to understand. They show us that even on our familiar blue planet, we're still discovering forms of life that seem to come from science fiction, reminding us that Earth itself is still capable of surprising us with wonders beyond our imagination. The midnight zone, life without light. There's a layer of the ocean where the very concept of day and night becomes meaningless, where creatures have lived for millions of generations without ever experiencing the warmth of sunlight or the rhythm of seasons. This is the midnight zone, formerly known as the bathypelagic zone, a realm that begins roughly 1,000 meters below the surface and extends down into crushing depths where darkness reigns eternal. Imagine living your entire life inside a windowless room, never knowing whether it's noon or midnight, summer or winter, never seeing colors as we understand them, never experiencing the natural cycles that govern almost all surface life. This is the reality for creatures of the midnight zone, and yet they've not only survived, but created one of Earth's most fascinating ecosystems. The transition into the midnight zone happens gradually, then suddenly, as you descend through the ocean's layers, the familiar blue-green light from above slowly fades, shifting through deeper and deeper shades, until it finally disappears entirely. By the time you reach 1,000 meters depth, the last traces of sunlight have been absorbed by the water above, and you enter a world of absolute darkness that has never been broken by natural light from the surface. Temperature in the midnight zone hovers just above freezing, typically between 2 and 4 degrees Celsius. There are no seasonal variations, no warm currents to provide relief from the cold, just constant, near-freezing temperatures that would kill most surface creatures within minutes. Yet, the animals here have adapted so completely to this cold that many would die if exposed to the warm temperatures of surface waters. Food in the midnight zone comes from above in a constant but sparse rain of organic matter, dead plankton, fecal pellets, and other biological debris that sinks down from the productive surface waters. Scientists call it marine snow, and it drifts down through the water column like a gentle blizzard of nutrition. But this marine snow is unpredictable and scarce, creating a feast or famine environment where creatures must be prepared to take advantage of any food source that presents itself. This scarcity has shaped every aspect of life in the midnight zone. Many creatures here have evolved enormous mouths relative to their body size, ready to swallow anything edible that might drift or swim within range. The black swallower, for instance, can unhinge its jaws and stretch its stomach to consume fish several times larger than itself. It's like having a stomach that can expand to accommodate a meal the size of a small car. Essential when you never know when your next meal might arrive. Energy conservation becomes a matter of survival. Many midnight zone creatures have evolved incredibly slow metabolisms, allowing them to survive on minimal food for extended periods. They move lowly and deliberately, expending as little energy as possible, while remaining alert for feeding opportunities. It's like living life in slow motion, every movement carefully calculated to preserve precious energy reserves. But perhaps the most remarkable adaptation is the widespread use of bioluminescence, the ability to create light through chemical reactions. In a world without sunlight, creatures have learned to become their own light sources, turning their bodies into living lanterns, spotlights, and communication devices. It's estimated that up to 90% of creatures in the midnight zone can produce their own light in some form. This bioluminescence serves many purposes. Some creatures use it for hunting, creating glowing lures to attract prey in the darkness. The atoll jellyfish creates a burglar alarm of light when attacked, producing a spinning ring of bioluminescence that might attract larger predators to eat whatever is attacking it. Others use light for communication, flashing patterns that might serve as mating calls or territorial warnings in the darkness. The midnight zone is home to one of the largest migrations on Earth, though it happens vertically rather than horizontally. Every night, millions of creatures rise from the depths toward the surface waters to feed, then return to the darkness before dawn. This daily vertical migration involves more biomass than any terrestrial migration, yet it happens largely invisibly in the darkness of the open ocean. Lanternfish are among the most numerous vertebrates in the midnight zone, their bodies covered with light-producing organs called photophores. These create patterns unique to each species, like living constellation maps that help individuals recognize their own kind in the darkness. When viewed from a submarine, schools of lanternfish look like underwater galaxies, points of light moving in coordinated patterns through the black water. The hatchetfish has evolved one of the most sophisticated camouflage systems in nature. Its belly is covered with light-producing organs that exactly match the faint light filtering down from above, making it invisible when viewed from below. It's like having a built-in LED array that automatically adjusts its brightness to match the background, creating perfect invisibility in a world where being seen means being eaten. Giant siphonophores drift through the midnight zone like living fishing nets, their transparent bodies stretching for dozens of meters through the water. These aren't single animals, but colonies of thousands of individual organisms working together, each specialized for different functions. Some for locomotion, others for feeding, others for reproduction. They're like underwater cities, coordinated biological communities that hunt collectively in the darkness. The midnight zone challenges our understanding of what it means to be alive. These creatures experience a reality so different from ours that they might as well inhabit another planet. They've never seen a sunrise, never felt warmth from above, never experienced the daily rhythms that govern surface life. Yet they've created complex ecosystems, intricate food webs, and evolutionary strategies that rival anything in the surface world. Perhaps most remarkably, many midnight zone creatures undertake daily journeys between their dark realm and the food-rich surface waters, making vertical migrations of hundreds of meters every single day. They live between two worlds: the productive but dangerous surface waters, where food is abundant but predators are everywhere, and the safe but scarce midnight zone where they can hide in darkness but must constantly search for nutrition. The midnight zone represents life's ability to thrive in conditions that seem utterly hostile to existence. It shows us that biology is far more adaptable than we ever imagined, that evolution can find solutions to problems that seem impossible. These creatures have turned the ultimate limitation, the complete absence of light, into an opportunity, creating their own illumination and building ecosystems that depend not on energy from the sun, but on the ingenuity of life itself. The silence below. Why sound is our only guide. In the deep ocean, where darkness swallows everything beyond arm's reach, sound becomes more than just noise. It becomes vision, communication, navigation, and survival, all rolled into one. While we surface dwellers live in a world dominated by light, creatures of the deep have learned to navigate reality through acoustics, creating an underwater realm where hearing replaces sight as the primary sense for understanding the world. Water carries sound differently than air, and these differences have shaped every aspect of deep ocean life. Sound travels about 4 times faster underwater than it does through air, and it can travel much farther without losing its intensity. In the deep ocean, where temperature and pressure create layers of different density, sound waves can travel for thousands of kilometers, bending and reflecting in ways that create acoustic highways across entire ocean basins. For humans, this acoustic environment is both alien and challenging. Our ears, evolved for air-based hearing, struggle to determine direction underwater. Sound seems to come from everywhere and nowhere simultaneously, creating a disorienting experience that leaves us acoustically blind even when our technology works perfectly. But for creatures born in this environment, sound provides a richness of information that we can barely imagine. Whales have become the masters of long-distance oceanic communication, their songs traveling across entire ocean basins. Blue whales produce calls at frequencies so low that they're at the edge of human hearing, and these calls can travel for thousands of kilometers through the deep ocean. It's like having a telephone system that spans continents, allowing whales to communicate with others of their species across distances that would take months to swim. But it's not just whales that use sound for communication. Many deep-sea fish produce sounds through various mechanisms, grinding their teeth, vibrating their swim bladders, or rubbing specialized body parts together. These sounds create an underwater symphony that scientists are only beginning to understand. Each species has its own acoustic signature, its own way of announcing its presence, attracting mates, or warning off competitors in the darkness. Echolocation, the biological sonar system perfected by dolphins and some whales, becomes even more important in the deep ocean. These animals send out clicks and whistles, then listen to the echoes to build detailed mental maps of their surroundings. They can see through sound, detecting not just the location of objects but also their size, shape, texture, and even internal structure. A dolphin can echolocate a fish and determine not just where it is, but what species it is, and whether it's healthy or sick. The deep ocean's acoustic environment is layered with natural sounds that create an underwater landscape of noise. The seafloor itself produces sounds, the grinding of sediment, the settling of rocks, the bubbling of underwater springs. Underwater avalanches create rumbling noises that can be heard for hundreds of kilometers. Volcanic activity produces sounds ranging from low-frequency rumbles to sharp cracks as new rock forms and cools rapidly in the cold water. Even more mysterious are the sounds that we can't yet explain. The ocean regularly produces acoustic phenomena that puzzle scientists. Strange calls, rhythmic patterns, and sounds so low frequency that they're felt more than heard. Some of these sounds are so powerful that they can be detected by monitoring stations thousands of kilometers away, yet their sources remain unknown. The famous bloop, a powerful ultra-low frequency sound detected by underwater microphones in 1997, created years of speculation about unknown deep-sea creatures before scientists determined it was likely caused by ice movement in Antarctica. But the bloop represents just one of many unexplained acoustic phenomena in the deep ocean, reminding us that there are still sounds in the depths that we cannot identify or understand. For scientists trying to study the deep ocean, sound becomes our most powerful tool for exploration. Since light can't penetrate more than a few hundred meters of water, and sending vehicles to the deep is expensive and time-consuming, acoustic monitoring allows us to observe the deep ocean from the surface or from great distances. Hydrophones, underwater microphones, can be placed on the seafloor to listen continuously to the acoustic environment, recording sounds from creatures, geological processes, and human activities. These listening posts create an acoustic picture of deep ocean life that reveals behaviors and interactions we could never observe directly. Scientists have discovered new whale species, tracked the movements of deep-sea animals, and detected underwater earthquakes and volcanic eruptions through acoustic monitoring. The deep ocean's acoustic environment also reveals the impact of human activity in ways that visual observation never could. Ship noise, industrial activity, and military sonar create acoustic pollution that can travel for thousands of kilometers underwater. Marine mammals that depend on sound for communication and navigation can be disrupted by human-generated noise, their acoustic world overwhelmed by the industrial sounds of surface activity. But perhaps most intriguingly, the deep ocean's acoustic environment suggests forms of communication and behavior that we're only beginning to understand. Complex soundscapes emerge from deep-sea communities, with different species contributing different acoustic elements to create what some scientists describe as underwater orchestras. These soundscapes change with the time of day, season, and location, suggesting that the acoustic environment of the deep ocean is far more structured and meaningful than we previously realized. In the deep ocean, silence itself becomes significant. The absence of sound can be as informative as its presence, indicating empty water, dead zones, or areas where human activity has disrupted natural acoustic patterns. Scientists have learned to read these silences, understanding that in an environment where sound is vision, the absence of acoustic activity can indicate ecological disruption or environmental change. The deep ocean teaches us that there are entire dimensions of reality that exist beyond our visual experience. In the depths where light cannot penetrate, life has learned to navigate through sound, creating acoustic realities as complex and meaningful as any visual landscape. For creatures of the deep, sound isn't just communication, it's their window into reality, their way of understanding and interacting with their world. As we continue to explore the deep ocean, we're learning to hear what the depths have always known, that sound carries information, emotion, and meaning in ways that our sight-dependent experience can barely comprehend. The silence below isn't empty, it's full of conversations, songs, and stories that we're only beginning to learn how to hear. The ocean's memory, sediments, wrecks, and forgotten time. The seafloor is Earth's ultimate archive, a vast library where every page is written in mud and time stretches back millions of years. While surface landscapes are constantly reshaped by wind, rain, and geological activity, the deep ocean floor preserves history with remarkable fidelity, accumulating layer upon layer of sediment that holds the story of our planet's past in startling detail. Imagine if every day of your life left a thin layer of dust on your floor, and no one ever cleaned it. Over years, you could read the story of your life in those layers. The day you got a pet, fur and dander. The week you were sick, tissues and medicine residue. The party you hosted, food scraps and confetti. The ocean floor works similarly, but on a timescale that spans geological ages. Marine sediments accumulate incredibly slowly, often just a few centimeters every 1,000 years. This means that a core sample just a few meters long can represent hundreds of thousands of years of Earth's history. Scientists who drill into these sediments are essentially time travelers, reading the chemical signatures and microscopic fossils that tell stories of ancient climates, extinct ecosystems, and long-forgotten environmental changes. Each layer of sediment holds clues about the conditions that existed when it was deposited. The types of microscopic shells found in a layer can indicate ocean temperature and chemistry from millions of years ago. The presence of certain minerals suggests volcanic activity or massive storms. Even the color of sediment layers can reveal information about oxygen levels, biological productivity, and climate conditions that existed when those particles first settled to the bottom. The deep ocean has preserved evidence of every major climate change in Earth's history. Ice ages leave distinctive signatures in sediment layers, as do periods of global warming, massive volcanic eruptions, and even asteroid impacts. The sediments hold evidence of the extinction event that killed the dinosaurs, of the ice ages that covered much of Earth in glaciers, and of warm periods when tropical forests grew, where tundra exists today. But the ocean's memory extends beyond natural history to include the relatively recent story of human civilization. Shipwrecks scattered across the seafloor serve as time capsules, preserving moments from human history with extraordinary detail. In the cold, oxygen-poor environment of the deep ocean, organic materials that would decay rapidly on land can be preserved for centuries or millennia. The Titanic, perhaps the most famous deep-sea wreck, sits on the Atlantic seafloor as a monument to a specific moment in human history. Despite being underwater for over a century, many details of the ship remain remarkably preserved. Personal belongings, ship's equipment, and even organic materials like leather and wood have survived in the deep ocean's preserving environment. Ancient shipwrecks reveal details about historical trade routes, shipbuilding techniques, and the daily lives of people from civilizations long past. Roman ships found in the Mediterranean carry cargoes that tell stories of ancient commerce. Viking vessels reveal the extent of Norse exploration. Each wreck is like a museum that sank intact, preserving not just objects but entire contexts that help us understand how people lived and traveled in ancient times. The preservation power of deep ocean sediments extends to scales both massive and microscopic. Whale falls. The carcasses of dead whales that sink to the seafloor can take decades to decompose in the cold, nutrient-poor deep ocean. These massive remains create temporary ecosystems, supporting specialized communities of scavengers and decomposers that depend on these rare windfalls of nutrition. Even more remarkably, the deep ocean preserves evidence of events that happened before humans existed. Sediment cores have revealed the patterns of ancient climate changes, showing how Earth's temperature and weather patterns have varied over millions of years. This information is crucial for understanding current climate change, providing a baseline against which to measure human impact on global environmental systems. The chemical composition of ancient sediments can reveal atmospheric conditions from the distant past. The ratio of different isotopes in sediment layers indicates ancient ocean temperatures with remarkable precision. The presence of certain compounds reveals information about atmospheric composition, including levels of carbon dioxide and oxygen that existed millions of years before humans began altering the atmosphere. Some of the most fascinating discoveries come from sediment cores that reveal catastrophic events from Earth's deep past. Layers of unusual sediment mark massive underwater landslides, volcanic eruptions that affected global climate, and even asteroid impacts that left chemical signatures in seafloor deposits. Each layer tells a story of change, disaster, recovery, and evolution that shaped the world we know today. The deep ocean also preserves evidence of life forms that no longer exist. Microscopic fossils embedded in sediment layers provide detailed records of how marine ecosystems have changed over time. These tiny remains reveal the rise and fall of different species, the impact of climate changes on ocean life, and the long-term patterns of evolution and extinction that have shaped marine biodiversity. Modern human activity is also leaving its mark in ocean sediments. Industrial pollutants, plastic particles, and radioactive materials from nuclear testing are being incorporated into sediment layers, creating a distinct signature that future scientists will be able to identify as marking the beginning of the Anthropocene, the geological age defined by human impact on Earth systems. The ocean floor's role as a keeper of memories extends to preserving evidence of human cultures that have been lost to time. Underwater archaeological sites reveal settlements that were flooded by rising sea levels, harbors that served ancient civilizations, and even entire cities that were claimed by the sea. These submerged archaeological sites are often better preserved than their terrestrial counterparts, protected by water from the weathering and human interference that destroys surface sites. Perhaps most poetically, the deep ocean preserves not just physical evidence but also sounds from the past. Hydrophones placed on the seafloor can detect acoustic signals that have been traveling through the ocean for decades, carrying the sounds of distant events across ocean basins. The ocean becomes an echo chamber, holding on to sounds long after their sources have disappeared. The sediments of the deep ocean represent one of Earth's most complete and detailed historical records, our archive that spans from the present day back to the earliest periods of our planet's history. Every grain of sand, every microscopic shell, every chemical signature preserved in these underwater archives adds another piece to our understanding of how Earth has changed over time, and how it might continue to change in the future. In the deep ocean's sediments, time moves slowly but preserves everything. The seafloor remembers ice ages and warm periods, mass extinctions and evolutionary radiations, the rise and fall of civilizations and the impacts of human activity. It's a library written in mud and time, holding stories that stretch back hundreds of millions of years, waiting patiently for us to learn how to read them. Why satellites can't see the ocean floor. From space, our planet looks like a smooth blue marble, its ocean surfaces reflecting sunlight in brilliant patterns that shift with waves and weather. Satellites orbiting hundreds of kilometers above can map continents in exquisite detail, track individual vehicles moving along highways, and detect changes in vegetation patterns across entire countries. Yet, when these same sophisticated instruments turn their sensors toward the ocean, they encounter an impenetrable barrier: the water itself, light, which carries the visual information that satellites depend on, behaves very differently in water than it does in air or the vacuum of space. When sunlight hits the ocean surface, several things happen simultaneously. Some light reflects off the surface like a mirror, some is absorbed by the water molecules themselves, and some penetrates into the ocean where it begins a journey that will end long before reaching the seafloor. Water absorbs different colors of light at different rates, which is why the ocean appears blue to our eyes. Red light, with its longer wavelengths, is absorbed almost immediately within the first few meters of water depth. Orange and yellow light don't travel much farther. Even blue and green light, which penetrate deepest into ocean water, can only reach down a few hundred meters under the best possible conditions before being completely absorbed. This means that in the clearest tropical waters, under perfect conditions, sunlight might penetrate 200 meters down, less than the height of a 60-story building. Compare this to the average ocean depth of nearly 4,000 meters, and you begin to understand the scale of the problem. It's like trying to use a flashlight to see the bottom of a well that's 20 times deeper than your light can reach. But the challenges go far beyond just depth. Ocean water is rarely perfectly clear. It contains dissolved minerals, microscopic plants and animals, particles of sediment, and countless other materials that scatter and absorb light. In coastal areas where rivers carry sediment into the ocean, or in regions with high biological productivity where microscopic life clouds the water, light penetration is reduced to mere meters instead of hundreds of meters. The ocean surface itself creates additional complications for satellite observation. Waves, currents, and weather constantly change the angle and intensity of light reflection from the surface. What satellites primarily see when they look at the ocean is the interaction between sunlight and the surface layer of water, not the water itself, and certainly not anything beneath it. Even if light could penetrate to the seafloor and return to the surface carrying visual information about bottom features, it would then have to travel back through hundreds of kilometers of atmosphere to reach the satellite's sensors. Atmospheric interference, clouds, water vapor, dust, and pollution would further degrade any signal that managed to make the round trip from satellite to seafloor and back. This physical limitation means that satellites can only provide indirect clues about seafloor topography. They can detect slight variations in the ocean surface that correspond to underwater features. Massive underwater mountains create tiny bulges in the ocean surface due to their gravitational pull, while deep trenches create almost imperceptible depressions. But these surface signatures are incredibly subtle, often just a few centimeters of elevation change across distances of many kilometers. The contrast with land mapping is striking. Satellites can create detailed maps of terrestrial landscapes because light bounces off surface features and returns to space carrying visual information about everything it encounters. Mountains, valleys, forests, and cities all reflect light differently, creating distinct signatures that satellites can detect and interpret. The ocean surface, however, acts like a one-way mirror. Light goes in, but useful visual information about the depths doesn't come back out. This is why we have detailed maps of Mars, Venus, and even distant moons, but only crude maps of our own ocean floor. Planetary surfaces can be mapped by satellites, radar, and other remote sensing technologies that work across the vacuum of space. Earth's ocean floor must be mapped laboriously, one sonar ping at a time, by ships that travel slowly across the surface while sending sound waves down to the bottom. The irony is profound. We can map the surface of planets, millions of kilometers away, more easily than we can map the seafloor just a few kilometers beneath our own ships. Space presents challenges, vast distances, extreme temperatures, radiation, but it doesn't absorb and scatter the electromagnetic signals we use for remote sensing. Water, on the other hand, is almost perfectly opaque to the kinds of energy that make satellite mapping possible. Recent technological advances have pushed the limits of what satellites can detect about ocean depths, but these improvements are incremental rather than revolutionary. Specialized satellites can now detect slightly more subtle variations in ocean surface height, providing marginally better indirect information about major seafloor features. But the fundamental physical barrier remains. Water absorbs light, and no amount of technological sophistication can change that basic fact. Laser-based satellite systems can penetrate slightly deeper than traditional optical sensors, but even the most advanced laser altimeters can only see a few dozen meters into clear water under ideal conditions. For mapping the deep ocean floor, laser systems face the same fundamental limitation as visible light. Water eventually absorbs all electromagnetic radiation regardless of its wavelength or intensity. The limitation extends beyond just mapping to all forms of satellite-based ocean floor observation. Satellites cannot directly detect seafloor geology, identify underwater volcanoes, locate shipwrecks, or observe deep-sea biological activity. All of these observations must be made by instruments that are actually in the water. Submarines, robotic vehicles, or sensors lowered from ships. This technological barrier helps explain why ocean exploration lags so far behind space exploration in terms of public awareness and funding. Satellite images of Mars rovers, or detailed photographs of Jupiter's moons, capture public imagination because we can actually see these alien landscapes. The ocean depths remain invisible to our most powerful remote sensing technologies, making them seem abstract and distant even though they're right beneath us. The inability of satellites to penetrate ocean water means that the vast majority of our planet's surface, the seafloor that covers more than 70% of Earth, remains hidden from our most sophisticated mapping technologies. We can see the rings of Saturn and the polar ice caps of Mars more clearly than we can see the mountainous landscape that lies beneath a few kilometers of seawater just off our own coasts. This fundamental limitation reminds us that despite all our technological achievements, the ocean still presents challenges that push the boundaries of what's physically possible. The water that makes Earth unique among known planets also makes much of our world invisible to us, creating one of the largest blind spots in our understanding of our own planet. Underwater mountains, taller than Everest. Have you ever climbed a mountain? Even if you've only walked up a steep hill, you know that feeling. Your breath shortening, your perspective expanding with each step higher. Now imagine a mountain so tall it would dwarf Everest, so magnificent it would leave you speechless, except it's completely underwater, invisible from the surface, unknown to most of the world. The ocean floor isn't flat like a bathtub. Bottom. It's wrinkled and folded like a blanket thrown over sleeping giants. Hidden beneath miles of water are mountain ranges that stretch for thousands of miles, peaks that rise from abyssal plains with the majesty of the Himalayas. The mid-Atlantic ridge, for instance, runs like a spine down the center of the Atlantic Ocean for over 10,000 miles, longer than any mountain range on land. These underwater peaks tell stories that began millions of years ago, when the Earth was young and restless. Picture the planet as a living thing, breathing slowly, its chest rising and falling over geological time, where tectonic plates meet and pull apart. Magma rises from deep within the Earth, like warm breath in cold air, creating new seafloor and building these submarine mountains grain by grain, eruption by eruption. Mauna Kea in Hawaii is technically the tallest mountain on Earth, not Everest. From its base on the ocean floor to its snow-capped peak, it measures over 33,000 feet. But Mauna Kea has the advantage of poking its head above water, becoming famous, earning a name. Think of all the unnamed peaks sleeping beneath the waves, taller than anything we celebrate on land. visited only by the occasional deep-sea creature drifting past like a slow-motion bird. These underwater mountains create their own weather systems in the deep. Ocean currents hit their slopes and spiral upward, carrying nutrients from the depths toward the surface like invisible elevators of life. Around their bases, strange ecosystems flourish in the perpetual darkness. Gardens without sunlight. Communities of creatures that have never seen a star. The pressure at these depths is crushing, literally hundreds of times greater than at sea level. It's like having the weight of 50 jumbo jets pressing down on every square inch of your body. Yet, life finds a way. Tubworms cluster around volcanic vents like underwater flowers, their bodies swaying in currents heated by the Earth's inner fire. Fish with transparent heads and glowing eyes patrol these slopes like gentle ghosts, adapted to a world where bioluminescence is the only light show in town. Scientists discovered these mountain ranges relatively recently. Most of our maps of the ocean floor are less detailed than our maps of Mars. We know more about the surface of the moon than we do about the deepest trenches in our own oceans. It's as if we've been living in a house for thousands of years, never bothering to explore the basement, never realizing that our foundation sits on top of geological cathedrals. And that brings us to something even more remarkable. These mountains aren't just sitting there quietly. They're alive with activity, connected to volcanic systems that reshape the ocean floor in ways we're only beginning to understand. Hidden volcanoes and submarine earthquakes. Imagine the Earth as a vast organism with a beating heart, made of molten rock. That heartbeat creates rhythms we rarely feel on land, unless we're floating above one of the most volcanically active places on the planet, the ocean floor. There are more active volcanoes under the sea than on all the continents combined. While you sleep tonight, underwater volcanoes are erupting in the darkness, sending plumes of superheated water and minerals into the deep like underwater geysers. These aren't the dramatic, explosive eruptions we see on land. They're gentler, more mysterious, creating landscapes that change while no one is watching. Picture lava flowing into water, colder than a winter night. It doesn't explode into steam. The pressure is too great for that. Instead, it forms pillow-like shapes, cooling rapidly into glass-like formations that look like frozen underwater bubbles. These pillow basalts carpet vast areas of the ocean floor, like a sculptor's dream made real, creating terrain that's both alien and beautiful. The ring of fire that circles the Pacific Ocean isn't just a ring of land-based volcanoes. It continues underwater, forming a necklace of volcanic activity that connects continents in ways early explorers never imagined. Submarine volcanoes along this ring create islands that rise from the depths, like Earth's slow-motion fireworks. Though most never reach the surface, they remain underwater mountains, their peaks crowned with volcanic gardens where life thrives in conditions that would be impossible anywhere else on Earth. These underwater eruptions trigger earthquakes that ripple through the ocean floor like sound waves through a liquid guitar string. The seafloor shakes and shifts, sometimes violently enough to create tsunamis that race across entire ocean basins at the speed of a jet airplane. It's humbling to realize that some of the most powerful forces on our planet operate in complete silence and darkness, witnessed only by creatures that have evolved to call these depths home. But here's where it gets wonderfully strange. Around these volcanic vents, life doesn't just survive, it throws a party. Hydrothermal vents spew water heated to temperatures that would instantly kill most life forms we know, yet they're surrounded by some of the most abundant ecosystems on Earth. It's like finding a tropical garden around a blast furnace, except the garden is made of creatures that seem designed by a dreamy imagination. Scientists only discovered hydrothermal vents in 1977. Less than 50 years ago. Before then, we assumed that all life on Earth ultimately depended on energy from the sun. But these vent communities taught us that life can feast on the Earth's own chemical energy, creating food from hydrogen sulfide and other compounds that would be toxic to us. It was like discovering that plants could photosynthesize darkness instead of light. The first researchers to see these vents through the portholes of research submarines described feeling like astronauts discovering life on another planet. Giant tube worms 6 feet long swaying in the current like underwater wheat. Ghostly white crabs scuttling across the volcanic landscape. Fish with antifreeze in their blood, perfectly adapted to waters that fluctuate between freezing and scalding. These discoveries changed our understanding of where life might exist elsewhere in the universe. If creatures can thrive around underwater volcanoes in Earth's deepest places, perhaps similar life flourishes around hydrothermal vents on the moons of Jupiter or Saturn, beneath ice sheets we've never seen. Interestingly, these underwater volcanic systems are also connected to something that's becoming increasingly important to our modern world: the deep-sea mining industry, where companies are beginning to eye the mineral treasures that volcanic activity has been depositing on the ocean floor for millions of years. The deep-sea gold rush. Mining the unknown. There's a gold rush happening right now, except the prospectors wear diving suits instead of 10-gallon hats, and their frontier lies miles beneath the surface of the sea. The ocean floor is carpeted with treasures that make the California gold rush look like pocket change. Nodules of precious metals scattered across the abyssal plains, like dragon's eggs waiting to be discovered. Imagine walking across a field covered with potato-sized rocks, except each rock contains copper, nickel, cobalt, and rare earth elements worth more than most people make in a year. These are polymetallic nodules, formed over millions of years as minerals precipitate slowly from seawater, layer by layer, like underwater pearls growing in the darkness. They sit on the seafloor like nature's own treasure chests, accumulated over geological timescales that make human civilization seem like a brief afternoon nap. The story of how these nodules form reads like a fairy tale, written by chemistry itself. In the deep ocean where no sunlight has ever penetrated, metals dissolved in seawater gradually crystallize around tiny seeds, sometimes a grain of sediment, sometimes a fragment of volcanic glass, sometimes even a shark's tooth. Over thousands of years, these nuclei attract layers of metals the way a snowball gathers snow, growing slowly in the eternal darkness until they become dense, dark spheres containing elements essential for modern technology. Your smartphone contains dozens of rare earth elements, many of which could theoretically be harvested from these deep-sea nodules. The batteries in electric cars, the superconductors in wind turbines, the magnets in computer hard drives, all depend on materials that lie scattered across the ocean floor in quantities that boggle the imagination. It's as if the entire ocean has been slowly, patiently, preparing for our technological age for millions of years. But here's where this modern treasure hunt becomes complicated, even melancholy. The deep sea floor isn't just a mineral warehouse, it's an ecosystem we barely understand. Those nodules provide habitat for creatures that might exist nowhere else on Earth. The sediments around them contain microbial communities that have been evolving in isolation for millions of years, creating forms of life that could hold keys to understanding how life itself began. Mining companies envision fleets of robotic collectors roaming the seafloor, like underwater combine harvesters, gathering nodules while trying to minimize damage to the surrounding environment. It sounds almost gentle, like berry picking in slow motion, but the reality is more complex. The deep-sea floor is a fragile archive of Earth's history, and disturbing it could erase stories written in sediment over millions of years. The creatures that live in these depths move slowly, reproduce rarely, and live for extraordinary lengths of time. Some deep-sea sponges are thousands of years old. They were already ancient when the first pyramids were built. Disturbing their habitat isn't like cutting down a forest that might regrow in decades. It's like erasing libraries that took millennia to write. And yet the irony is inescapable. The metals we need to build renewable energy systems and reduce our impact on Earth's climate lie hidden in one of Earth's most pristine and least understood environments. It's as if the planet is asking us to make a choice: harvest the materials we need for a sustainable future, or preserve the mysterious ecosystems that have remained unchanged since before humans walked upright. Some scientists propose that we need to understand these ecosystems fully before we disturb them. Others argue that climate change is so urgent that we can't afford to wait. It's a debate that plays out in conference rooms and research papers, but it's really about something deeper: how we balance our immediate needs against the preservation of mystery, how we weigh what we know against what we might never discover if we're not careful. Speaking of things we might never discover, the deep ocean is home to creatures so extraordinary that they challenge our very definitions of what life can be: gigantic squid and myths that came true. For centuries, sailors told stories that sounded like fever dreams. They spoke of sea monsters with eyes the size of dinner plates and tentacles longer than ship masts, creatures that could drag entire vessels into the abyss without a trace. Landlubbers dismissed these tales as the fantasies of men who'd spent too long at sea, too long staring at endless horizons under too much sun. The sailors were right. The giant squid, Architeuthis ducks, is real. And it's everything the old stories promised and more. Imagine a creature that can grow to the length of a school bus, with eyes larger than human heads, the biggest eyes in the animal kingdom, evolved to capture the faintest traces of light in the eternal darkness of the deep. Its tentacles are lined with suckers ringed with sharp, rotating hooks that can grip prey with a strength that would humble any human athlete. But even the giant squid has been overshadowed by its larger, more mysterious cousin, the colossal squid, Masonicochithus hamiltoni. While giant squids are built for speed, streamlined hunters that dart through the water like living torpedoes, colossal squids are built like underwater tanks. They're shorter than giants but much heavier, with hooks on their tentacles that rotate like can openers and bodies designed for the crushing pressures of the deepest waters. These creatures exist in a realm so remote that we've never observed one alive in its natural habitat. Everything we know comes from specimens that wash ashore dead, or from the scars found on sperm whales, the only predators brave or foolish enough to hunt these monsters in the deep. The battles between sperm whales and giant squids play out in absolute darkness, miles beneath the surface, like myths being written in real time. Picture the scene. In the crushing darkness 2 miles down, a sperm whale descends on a hunting dive that can last over an hour. Its sonar clicks echo through the water, painting a sound picture of the world below. Somewhere in that darkness, a giant squid waits, perhaps attracted by bioluminescent prey, perhaps simply existing in that patient way of deep-sea creatures. When they meet, the encounter is brief but epic, a contest between the largest brain on Earth and one of the most alien intelligences in our oceans. Squid intelligence is utterly unlike our own. They have distributed brains, clusters of neurons throughout their bodies, including in their arms. In a sense, each tentacle can think for itself. They can change color and texture instantly, not just for camouflage but for communication, their skin becoming a living display screen that broadcasts emotions and intentions in languages we're only beginning to decode. But giant squid aren't the only mythical creatures that have turned out to be real. The ocean has a way of making legends come true. Mermaids became dugongs, and manatees when seen from a distance by homesick sailors. Sea serpents might have been glimpses of giant oarfish, ribbon-like creatures that can grow to 30 feet long and swim through the water with undulating grace, their bodies catching light like living silver. The bioluminescence that seemed supernatural to ancient mariners, ships surrounded by ghostly glowing water or strange lights beneath the waves, turned out to be even more magical than the myth suggested. Countless microscopic creatures can produce their own light through chemical reactions, turning disturbed water into liquid starlight. On calm nights in certain parts of the ocean, every movement of a swimmer or a boat leaves a trail of blue-green fire, as if the sea itself were dreaming in light. Deep-sea creatures have evolved bioluminescence into an art form. The vampire squid, which despite its name is actually quite gentle, can turn itself inside out when threatened, covering its body with bioluminescent photophores that create a light show more spectacular than any fireworks display. Jellyfish drift through the depths like living lanterns, their bells pulsing with ethereal light. Anglerfish dangle glowing lures in front of their mouths like living fishing rods, attracting prey in the darkness. These aren't just random biological curiosities, they're solutions to the fundamental challenge of life in the deep. How do you find food, mates, or safety in a world without sunlight? Bioluminescence becomes a language of survival, a way of writing messages in light against the infinite darkness. But the deep ocean doesn't just contain strange creatures, it also contains phenomena that challenge our understanding of what's possible underwater, including something that sounds like science fiction but is absolutely real: underwater lakes and rivers. A world within a world. Imagine diving deep into the ocean, deeper than sunlight has ever penetrated, and suddenly discovering a lake. Not just any lake, but a perfectly formed body of water sitting on the seafloor, complete with a distinct shoreline where the underwater lake meets the surrounding seawater. It sounds impossible, like a dream within a dream. But these underwater lakes are real, and they're among the most surreal phenomena our planet has to offer. These are called brine pools, and they exist because water, like everything else in nature, comes in different densities. The lakes are formed by water so saturated with salt and other minerals that it's much heavier than regular seawater. This dense brine settles into depressions on the seafloor like liquid mercury, creating distinct boundaries that behave exactly like the surface of a terrestrial lake, except everything is already underwater. Picture a research submarine descending through the darkness, its light suddenly illuminating what looks like a perfectly ordinary lakefront scene, complete with a shoreline where visitors might expect to find a beach. except the beach is the ocean floor, and the air above the lake is actually seawater, and the lake itself is brine so toxic that it would kill most sea creatures instantly. It's like discovering that Russian nesting dolls extend to entire ecosystems. Water within water within water, each layer with its own rules and residents. Fish swimming too close to these brine pools can become disoriented, their buoyancy systems confused by the sudden change in water density. Sometimes they fall into the brine like drunk drivers veering off a cliff, and the hypersaline water pickles them instantly. The shorelines of these underwater lakes are sometimes littered with the perfectly preserved remains of sea creatures that made the fatal mistake of swimming too deep into the brine, like an underwater museum of poor navigation decisions. But life, as always, finds a way to turn even the most hostile environment into a home. Around the edges of these toxic lakes, bacteria thrive in conditions that would sterilize most environments. These microorganisms have learned to feed on the chemicals that make the brine pools so deadly to other life forms, creating ecosystems that exist at the very edge of what we consider possible. Some brine pools bubble with gases escaping from the seafloor, creating underwater hot tubs that would be lethal to visit. Others are perfectly still, their surfaces creating mirror-like reflections that double the eeriness of an already surreal scene. The largest known brine pool sits in the Gulf of Mexico, covering an area larger than a football field and reaching depths of 12 feet. A substantial lake by any measure, except that it happens to exist on the bottom of the ocean. But underwater lakes aren't the only impossible waterscapes hidden in the deep. There are also underwater rivers, streams of dense water that flow across the seafloor, following the contours of underwater valleys and canyons. These rivers can flow for hundreds of miles, carrying sediments and nutrients across the abyssal plains like liquid conveyor belts, creating currents within currents in a three-dimensional flow system that makes the Amazon River look simple by comparison. The largest underwater river flows through the Black Sea, carrying Mediterranean water along the seafloor for over 1,000 miles. If this river existed on land, it would rank as the 6th largest river in the world by volume. But instead of carving canyons through rock, it flows invisibly through the deep, its presence known only to scientists with sophisticated instruments, and the occasional deep-sea creature that has learned to ride its currents like an underwater highway. These phenomena remind us that the ocean isn't just a big bathtub filled with salt water. It's a complex, layered world where water itself comes in different flavors, densities, and temperatures, creating internal weather systems and geography that we're only beginning to map. It's like discovering that the atmosphere has secret rooms we never knew existed, or that clouds can form their own clouds in ways we never imagined. And speaking of things we never imagined, the ocean's complexity becomes even more apparent when we consider how much of it remains completely unknown to us, making it in many ways more mysterious than the vacuum of space itself. The last frontier, how the ocean compares to space. We've all seen the images. Rovers trundling across Martian landscapes, satellites capturing the rings of Saturn, telescopes peering into galaxies billions of light-years away. Space exploration captures our imagination, because it represents the ultimate frontier, the great unknown that calls to our deepest sense of adventure. But here's a perspective that might surprise you. We know more about the surface of Mars than we do about the bottom of our own oceans. Think about that for a moment. We've mapped every crater on the Moon with stunning detail, but more than 80% of our ocean floors remain unmapped at the same resolution. NASA's budget for space exploration typically runs into tens of billions of dollars annually, while ocean exploration receives a tiny fraction of that funding. It's as if we've decided to explore our neighbor's house thoroughly while ignoring entire wings of our own home. This comparison isn't meant to diminish space exploration. It's genuinely awe-inspiring and scientifically crucial, but it highlights something profound about human psychology. We're drawn to the distant and exotic, while overlooking the mysterious that lives right here on our own planet. The ocean depths are as alien as any extraterrestrial landscape, populated by creatures that seem designed by a science fiction author, and governed by physics that challenge our terrestrial intuitions. Consider the practical differences between exploring space and exploring the deep ocean. In space, the main challenge is the vacuum, the absence of everything. Spacecraft need to carry their own atmosphere, their own pressure, their own everything. But in the deep ocean, the challenge is the presence of too much of everything. Crushing pressure, corrosive salt water, and complete darkness that makes even simple observations difficult. A spacesuit protects an astronaut from the vacuum of space, by maintaining 1 atmosphere of pressure inside, about 14 pounds per square inch. But a deep-sea diving suit must protect against pressures that can exceed 1,000 times that amount. At the deepest parts of the ocean, the pressure is equivalent to having 50 jumbo jets stacked on top of every square inch of your body. Materials that work perfectly in the vacuum of space crumple like paper bags in the deep ocean. Yet both environments host forms of exploration that push the boundaries of human engineering and scientific understanding. Both require specialized vehicles that cost millions of dollars and years of development. Both offer the possibility of discoveries that could change your understanding of life itself. The difference is that space exploration gets the Hollywood treatment, while ocean exploration happens in a darkness so complete that most people never think about it at all. Here's what makes ocean exploration uniquely challenging. Space is mostly empty, which makes navigation relatively predictable. You can plot a course to Mars and expect to find it roughly where your calculations suggest it should be. But the ocean is a three-dimensional fluid environment where currents shift, temperatures fluctuate, and the landscape itself can change due to underwater earthquakes, volcanic eruptions, or even the slow drift of sediments. It's like trying to navigate through a house where the rooms rearrange themselves while you're walking through them. The life forms we might discover in space are purely hypothetical at this point, but the deep ocean is teeming with actual alien-like creatures that exist right now. We regularly discover new species in the deep, not just variations on familiar themes, but fundamentally different approaches to being alive. Some deep-sea bacteria live off chemical energy in ways that were unknown to science until recently. Some creatures have evolved to survive in conditions so extreme that they expand our definition of what environments can support life. This has profound implications for astrobiology, the search for life beyond Earth. Every weird creature we discover in Earth's oceans expands the range of conditions where we might expect to find life elsewhere in the universe. The hydrothermal vents on Europa, one of Jupiter's moons, might host ecosystems similar to those around underwater volcanic vents in our own oceans. The subsurface ocean beneath the ice of Saturn's moon, Enceladus, could contain life forms similar to the bacteria that thrive in Earth's deepest trenches. In a way, ocean exploration is space exploration. It's just space exploration that happens to be closer to home. Both push us to develop new technologies, both challenge our assumptions about what's possible, and both offer the promise of discoveries that could change everything we think we know about our place in the universe. But the ocean's influence on our planet extends far beyond the creatures that live in its depths. The deep waters play a crucial role in systems that affect every breath you take, and every day of weather you experience. The deep's role in climate and weather. Every breath you take has been touched by the deep ocean. Every raindrop that falls, every breeze that cools you on a summer day, every snowflake that melts on your tongue, all of these are connected to processes that begin miles beneath the surface of the sea, in places where no sunlight has ever penetrated. The ocean is our planet's great circulatory system, and like the circulatory system in your body, much of the most important work happens out of sight. While we notice the waves and tides at the surface, the real action takes place in the deep, where massive currents move water around the globe, like a slow-motion river system that spans entire oceans. Imagine the ocean as a vast, three-dimensional conveyor belt. Cold, dense water sinks in the polar regions near Greenland and Antarctica, beginning a journey that can last hundreds or even thousands of years. This deep water carries oxygen and nutrients as it flows slowly along the ocean floor, traveling from the North Atlantic to the Southern Ocean, then spreading into the Pacific and Indian Oceans like underground rivers flowing through liquid space. Meanwhile, warmer surface water moves in the opposite direction, carrying heat from the tropics toward the poles like a planetary heating system. This global circulation pattern, called the thermohaline circulation, thermo for temperature, haline for salt, regulates Earth's climate in ways that make the difference between our planet being habitable and being a frozen rock orbiting the sun. The Gulf Stream, which brings warm water from the Gulf of Mexico toward Europe, is just the surface expression of this deep circulation. Without it, London would have a climate more like Siberia. Despite being at the same latitude, the warm water that makes Western Europe temperate comes from depths where pressure could crush a submarine, driven by temperature and salinity differences that create density gradients spanning entire ocean basins. But here's where it gets both fascinating and slightly concerning. This system can change. Paleoclimatologists, scientists who study ancient climates, have found evidence that the thermohaline circulation has slowed down or even shut down completely in the past. leading to rapid climate changes that transformed entire continents within decades. It's like discovering that your planet's air conditioning system has an off switch, and it's been flipped before. The deep ocean also acts as a massive carbon reservoir, storing about 50 times more carbon than the atmosphere. As surface water cools and sinks, it carries dissolved carbon dioxide into the depths where it can remain for centuries or millennia. This process, called the biological pump, helps regulate the amount of carbon dioxide in our atmosphere, but it works slowly, on timescales that dwarf human lifespans. Ocean currents in the deep also help distribute nutrients around the globe. When deep water rich in nutrients eventually upwells to the surface, often along coastlines or in the middle of oceans where currents diverge, it fertilizes marine ecosystems, supporting the phytoplankton that form the base of ocean food webs. These microscopic plants also produce more than half the oxygen you breathe, making them some of the most important life forms on the planet, despite being invisible to the naked eye. The temperature of deep ocean water also affects sea level in ways that might seem counterintuitive. Water expands when it warms up, so as climate change warms the oceans, even the deep oceans, the total volume of seawater increases. This thermal expansion accounts for about half of current sea level rise, with melting ice contributing the rest. It's a slow process, but like many slow processes involving the ocean, it's also inexorable once it gets started. Perhaps most remarkably, the deep ocean acts as a climate time machine. Ice cores from glaciers can tell us about atmospheric conditions from thousands of years ago, but deep ocean sediments preserve records of Earth's climate going back millions of years. Scientists can drill cores from the seafloor and read Earth's climate history layer by layer, like examining tree rings, but on geological timescales. These sediment cores have revealed that Earth's climate can change much more rapidly than we once thought. Sometimes the planet has warmed or cooled by several degrees in just a few decades, changes that were driven by shifts in ocean circulation patterns. It's a reminder that the ocean, for all its apparent stability, can surprise us with changes that reshape entire civilizations. And speaking of surprises, the deep ocean has a way of producing sounds and phenomena that challenge our understanding in unexpected ways. Unsolved sounds, the bloop and other oceanic mysteries. In 1997, underwater microphones positioned throughout the Pacific Ocean detected something that shouldn't have existed, a sound so loud and so unusual that it captured the imagination of scientists and mystery lovers around the world. They called it the bloop, a name that sounds almost comically mundane for one of the ocean's most intriguing puzzles. The bloop was captured by hydrophones originally designed to detect Soviet submarines during the Cold War. These underwater listening devices are incredibly sensitive, capable of detecting sounds from thousands of miles away. The network of hydrophones, called ESA Sound Surveillance System, had been monitoring the oceans for decades, but they had never recorded anything quite like the bloop. Picture the sound. It started low, rose in frequency, then faded away over the course of about a minute. When scientists played it back at 16 times normal speed to bring it into the range of human hearing, it sounded remarkably like a living creature, something enormous calling out across the depths. But here's what made it so mysterious. It was far louder than any known biological sound, and it came from one of the most remote parts of the Pacific Ocean, miles from any known shipping routes or human activity. The bloop sparked theories that ranged from the scientific to the fantastical. Could it have been an unknown species of gigantic sea creature, something even larger than blue whales? Some speculated about colossal squid, or undiscovered species of deep-sea leviathans. Others wondered if it might be geological, the sound of underwater landslides or volcanic activity. The most creative theories involved everything from secret military experiments to sea monsters that had somehow escaped scientific detection. For years the bloop remained unexplained, a genuine mystery from the depths that reminded us how much we still don't know about our own planet. Scientists analyzed and reanalyzed the recordings, compared them to known biological and geological sounds, and came up empty. It was like having a recorded conversation with something unknown, but not being able to identify who or what was talking. The mystery was finally solved in 2005, but the answer was almost as remarkable as the theories it replaced. The bloop, it turned out, was the sound of an iceberg breaking away from an Antarctic ice shelf, a process called icequake. The sound was so loud because ice shelves are enormous, and when they crack and break they release energy equivalent to small earthquakes. The sound waves travel thousands of miles through the ocean before being detected by the hydrophones, creating one of the most distant eavesdropping events in scientific history. But the bloop is just one of many mysterious sounds that the ocean produces. There's upsweep, a sound that rises in frequency and has been detected continuously since 1991, possibly coming from underwater volcanic activity. There's whistle, a narrow-band sound that appears and disappears unpredictably. There's train, which sounds exactly like its name suggests, like a distant locomotive chugging through the depths. Some of these sounds have been explained, others remain mysteries. The ocean is constantly producing sounds that we're only beginning to understand. The songs of whales that can travel across entire ocean basins, the clicks and calls of dolphins creating three-dimensional sound pictures of their environment, the grinding and groaning of ice as it moves and breaks in polar regions. But perhaps the most intriguing aspect of ocean acoustics isn't the sounds we can identify, it's the vast realm of sounds we can't hear at all. Many ocean creatures communicate using infrasound frequencies below the range of human hearing. These low-frequency calls can travel for thousands of miles underwater, allowing creatures to communicate across distances that would be impossible on land. Blue whales, for instance, can probably hear each other across entire ocean basins, making the Pacific Ocean about as acoustically intimate as a small room. The deep ocean also produces sounds that exist at the very edge of our detection capabilities. There are whispers and murmurs that might be geological processes we don't understand, biological activities we've never observed, or interactions between water and seafloor that create acoustic signatures science hasn't yet decoded. Every time we deploy new, more sensitive hydrophones, we discover new layers of the ocean's acoustic environment, conversations and signals that have been happening all along, just outside our ability to eavesdrop. These acoustic mysteries remind us that the ocean is not a silent world. It's full of conversations, calls, and communications that create a three-dimensional soundscape, more complex than any symphony ever composed. Most of these sounds happen without any human witness. In a realm where acoustic signals carry information across distances that dwarf our terrestrial communication networks, and sometimes, these acoustic signals help us discover something even more remarkable than mysterious sounds. They help us find traces of human civilization that time and tide have claimed for the deep,